is this other one. You can see that in your book. And then B is down there. Okay? So if we would let this drop, what I called some delta 4, because it's on a 4-inch radius, then, and this is fixed to the top up here, so this is going to pivot right around its center, like this. This point is going to drop what I called delta 3. That delta 3 is going to show up down here as delta 3. And while that's occurring on that edge of this lower pulley, this edge over here on the upper pulley has to match delta 4, getting raised up. This has to go up delta 4. And so when I made my comments a moment ago that you weren't able to follow from my micro drawing there, is this line is offset slightly. And so therefore this body is going to move right here by something I could call delta B. Now this delta B down here is going to be the average of these two. The average of these two.
Why must it be?
Not the difference. It's the average, not the difference.
The reason it's the average is because there's a span here of 7 inches, and so we're talking about right in the middle. In other words, what's the y value? Imagine like when I'm teaching an algebra class, I talk about, well, how do you find the average of 2 test scores? You add them together and divide by 2, right? So same thing going on here. You're averaging these y values together to find that value in the middle. Okay? Now, if you want to play geometry, you can sit here and spin your wheels for a moment, or spin the pulleys, to try to figure out what that is, then it's going to take more work. But just going ahead and figuring out the average of the two, which I've penciled out in the book there. I don't know if you can see my writing. Can you see that on the left over there? Let me see if I can get that to lay a little flatter. That's not showing up too well. Let me just write it down. If I look at the upper pulley up here, I'll just copy what I wrote so I don't mess it up. Delta 3 is to 3, as delta 4 is to 4 for the top pulley, because this is a 3 and 4 inch radius, and one's opposing the other. If this goes up, that's going down. So these are the two that I'm concerned with right here. It's because these two relate to the lower pulley. You can see why I didn't want to use this differential approach on the previous problems that we talked about. But on this one, this is what they suggested. So then I wrote that delta 3 is going to be equal to negative 3/4 of delta 4, which is equal to, this implies negative 3/4 of y sub a double dot, if I would differentiate then. Because delta 4 relates to the motion of the body on the right over here, cylinder A. Now, if you look down here at the lower pulley, move that up a little bit. Here's the analysis on the lower pulley. And so this delta B is equal to, in the middle here, is the average of these readings. And I write that as delta 4 plus the negative 3/4 of delta 4 over 2, the average of those two. And that gave me a reading of 1/8 of delta 4, which is 1/8 of delta A. And so therefore, the acceleration of cylinder B, the second derivative on that delta, is going to be equal to 1/8 of the acceleration on A, which is 1/8. I think they gave us a positive 2 on that.
Yeah.
And then we end up with 1/4 meter, oh, excuse me, foot per second squared. And let's see. And that's positive, which was upward. Okay. Now, this is not the approach that I used with you on all the previous problems, though. So what I did separately is I went ahead, and if you can see it here in my notes, I went ahead and wrote down how I would modify the length of the cable. Can you see that? Let me go ahead and erase this and write it up here so you can see it a little better. Back over here, the key was seeing this piece right here. The fact that a portion of that strand of cable that was wrapped up along here over the top is actually going to then come on down. So what I had to do is I had to be careful when I wrote my equations. I think I called this y sub b here. And then we have the other body that's hanging down over on the right. And I have it called y sub a over on the far right. And so to write the cable equation then, you can see that we have, it looks like a pair of strands of y sub b. We have one strand of y sub a, but then we also have that little piece of cord that's getting unwrapped off that top cylinder, off that top pulley, and I call that delta 3. And then we have some constants on there. And if you crank this on down to the second derivative, we get this relationship equals 0. And then we have to look in there and see that we have to replace this piece. You actually have to look at this upper pulley here to be able to get, let's let the camera change. Okay, you have to look at this upper pulley here to get this relationship between the delta 3 and delta 4, which connects you to the other body. And that's the relationship we have right here. So delta 3 gets replaced with negative 3/4, and that implies actually this acceleration term becomes negative 3/4 of the acceleration of A. Is that okay with people? So watch out for little things like that. If I'm not going to throw this at you on an exam, this kind of a thing, but if you go move on into upper division dynamics courses or doing some things in robotics or cable type of things, just be careful on what you're up to there. If you've got some kind of a spool where something's wrapped on the spool, make sure you account for it. So if you tidy this up, you'll get the same answer, okay? Which I penciled out there in the book. Okay. That covered constrained motion reasonably well. Okay. So the way that you're going to tackle all the problems that I had assigned is to write the equation for the length of cable and then crank it out from there.
See that length is conserved.
So it's going to equal 7
solve it,
Right.
whatever it's made out of.
Exactly, yes. Okay. Let's now go ahead and look at Newton's second law. So we're ready to actually move into the next chapter where we start talking about the kinetics of particles now. And what we're going to do is we're going to look at Newton's second law, and then we're going to start working some problems with using equations of motion. So Newton observed that the acceleration acting on a particle is directly proportional to the applied forces. The acceleration acting on a particle is directly proportional to the applied forces. Now notice I'm using vector notation here. The constant of proportionality here, to make this into an equation then, is the reciprocal of something we call the mass. And so what this yields, the way that we traditionally see this, is that the sum of the forces, and I'm going to go ahead and use sigma there, the sum of the vector forces is equal to the mass of an object times the acceleration being experienced by the object. So this is the governing equation, and we're going to spend a few weeks now looking at this in different ways. We have 3 coordinate systems available to us. We have motion that might be called unconstrained motion, and then other types of problems that might be called constrained motion. So, and we're going to look at all those different types of conditions. Now, there are 2 types of problems here. It's pretty obvious if you look at this equation. You've got to know something here. We're going to know the mass in just about all the problems we're tackling. Oh, what is mass? If somebody came up to you and say, I'm just starting taking physics or something, and boy, this thing they keep talking about is mass. What is mass?
It's an object resistant to change in motion. I don't really know what it is, though. They just know its properties.
Yeah, its properties. The way I like to think of it is it's a resistance to change in motion. It's an inertia. It's an inertia. And I think, Dylan, I think you said something
That's
almost
exactly
like that.
what I said.
Very good. I just said what you said. Okay. So it's a resistance to change in motion. Now, in the sense of inertia. Now, when you hear the word inertia, you usually are thinking about what kind of motion? From your background in physics and things.
Like
Inertia. Most people think
rotation.
of rotational inertia, kind of a resistance to rotation. And I remember when I was a little kid, I can remember this vividly because I was about 6 or 7 years old, and we had a hill behind the place we lived, and we had an old automobile tire. One of my buddies was up the hill with a tire, and he rolls it down the hill. Well, I'm standing here with a broomstick, and I'm going, I'm just going to stick that in there and stop that. Okay, so it comes rolling down the hill, and I stick my broomstick in there in the tire, and you know what happened? The broomstick just went flying right out of my hand, and the wheel just went on down across the street and, whacked into a tree or something. Okay, that's my first experience where I was very conscious about inertia. Okay. Other experiences were getting punched in the nose. Okay. There's my body, my head had resistance to motion. Okay. So those kind of things. So mass, if you've played sports, played football or soccer or something where you run into somebody else, you feel pretty good if you're quite a bit bigger than that other person and you run into them, you just kind of run over them. Okay. But you don't feel so good if you're not quite as big as that other person. Okay. So think of it as a resistance to change in motion. Resistance to change in motion. So there's two types of problems. If we know the mass, then we may have some information that we could figure out what the acceleration is. Maybe that's prescribed information. Known acceleration. Or that could be obtainable through the kinds of problems that you've been studying already. Okay, so you might be able to obtain that. And then once you obtain that acceleration, then you could figure out what forces created that motion through Newton's second law. The other type of problem would be what? Yeah, if you know the forces that are acting on a particle, creating an unbalanced force, something non-zero in the vector sum of forces, if that's known, then you can plug that in here. You then have a description of the acceleration, and then from that acceleration, you can do what? Well, you could carry out your math that you've been learning the last few weeks, and you could figure out potentially the velocity and maybe even the location of where the particle might be after it's been subjected to some known forces. So those are the two fundamental types of problems. And then as I mentioned a couple minutes ago, we have unconstrained motion, such as
just like kicking a soccer ball or something.
Projectile would be a real simple case, and you've done some kinetics with that stuff already. Okay. Okay, etc. And then we have another, and then there's other types, obviously. And then there's constrained motion. What could be an example of that?
Something sliding along a surface.
Okay.
From a rope.
Yeah, something on a smooth surface. If it's on a smooth surface, then and it stays on that surface, there's no unbalanced forces vertically. Now let's say I have a tabletop here, and I have the object on the tabletop. Newton tells us that there's a certain force exerted downward by that mass, which is mass times the acceleration being experienced by the particle, which is g, mg, weight. What's counteracting that weight? The normal force, the surface of the tabletop pushing up against it. Those forces are equal to 0. Is there any acceleration? No acceleration in that direction. Then on that surface, this object could have some unbalanced forces. Could be a little rocket on there, maybe a couple different forces. Maybe it could be some ropes hooked on it. You may have done something in a lab, in a physics lab, where you had a variety of forces on a tabletop surface pulling in different directions, and then figured out what's going on to cause that object to move off in a certain direction or something. Okay? So there'd be unbalanced forces in 2 dimensions. Now we could go into 3D as well, and you could be talking about an amusement car ride that travels some prescribed path, constrained motion. Okay. So we have constrained types of problems and unconstrained problems, and then as I mentioned earlier, the 2 types, either known acceleration information or related to acceleration information, or having some information known about the forces. So, next step is we start working problems. So if we have a sum of vector forces is equal to a mass times acceleration, then these accelerations could be prescribed to us in which coordinate system would be best to start?
Rectangular.
Probably rectangular. We like that one. Okay. So what we might have is the sum of forces x equals the mass times the acceleration in the x direction, which would be mx double dot. Notice this is a scalar equation, and we have a vector equation up here. And now we're talking scalar. And we could go sum of forces y, mass times AY, and then sum of forces, if we're in 3D, okay, so here's your rectangular approach. We could just as well do this in cylindrical coordinates, right? We could do cylindrical coordinates. And develop the problem. And I don't have enough room on this board to write that out, but you're going to have your, and actually I can't break it up into AY, XY, Z like this anymore, so I shouldn't even put cylindrical on there. I have to go back up here to do the description. If I come back up here to do the cylindrical, then I would have to have my mass times my vector described in cylindrical, which would have an AR hat plus an A theta theta hat plus an AZ K hat. And we've been practicing problems with those type of descriptions for acceleration. We could do spherical. I don't think we're going to do many of those, though. Okay? So I think we're ready to actually start working some problems, and we have 40 minutes or so left today to work some problems out. Now, you're all familiar with doing this ever since you started physics, but you'll see, as you've seen already this term, that the kinds of engineering problems we come up with, oftentimes you have to sit there and really puzzle them out a little bit, do some extra sketching to work them out, that kind of thing. Now, you've taken statics. Most of you have taken strength of materials, and now you're taking dynamics. What's one of the most important things that you have to draw when you're doing these kind of problems? Okay, that's ingrained in your brain. Okay. Free body diagrams. Absolutely critical. So what you put on there is you put all of the forces that are acting, you put all of the forces that are acting on the object, and they could be constraints, okay? They could be the weight, mg. And what do you not put on that free body? You don't put the dynamic forces on there. What are the dynamic forces? What are the dynamic forces? This. Don't put that on your free body diagram. Now there is an approach that's taken in some textbooks where you actually draw that on there and write your equations as if they're statics equations. And you might pick up a book like that someday. What's going on in those books is they move MA over to the other side of the equation and make this equal to 0. So they treat it as a pseudo-statics kind of problem. Sum of forces minus MA equals 0. We don't do it that way. This is a much more powerful approach. It also is going to lend itself nicely to when we move into work and energy and impulse momentum. Okay. So let's go ahead and grab a problem so we can get our feet on the ground here. There's some nice discussion I would encourage you to read in the opening part of this chapter. Several pages there. And they begin then with the rectangular equations that I've already given you, you've seen before. and then they get to a nice variety of problems. So I think the first problem we might tackle, let's do one just to bring you back up to speed with some old skills you might have. Let's take one like number 13 down here. Notice there's a little bit of friction. There's a little bit of friction.